Welcome. In this session in linear data analysis, we'll solve this problem, which is that we're given basis vectors a1 and a2, and they're linearly independent, so they form a basis of a 2D vector space V. We're given a new vector c, and previously we established that we could formulate an error vector, which was the difference between the given vector c and a vector p, which was the nearest vector in the vector space to the new vector. And we had a governing equation, which was that A transpose E has to equal the zero vector. Let's now expand this using these terms and solve it. If I now substitute A transpose, if I substitute C minus P, then that still has to equal the zero vector. I can now distribute the matrix A over this vector summation, and I get A transpose C minus A transpose P equals 0. And I can now take A transpose P to the other side, and out of a convention, I will keep the P, which is the unknown, on the left side of the equation. So that would mean A transpose P has to equal A transpose C. And what is P? Well, I previously derived P as being the product of the matrix formed from the basis vectors and the unknown weight vector. And that implies that A transpose times A times W equals A transpose times C. And if we bracket this known matrix, the question is, can we solve this linear equation? Because now we have a simple linear equation, which is that a known matrix times an unknown vector equals a known vector. And the question is, does this have a solution? So let's observe that from the singular value decomposition, I can write A as an orthogonal matrix U times a singular value matrix times an orthogonal matrix V transpose. And that means that A transpose A, when I work this through, has to equal V times sigma squared times V transpose. And this is a symmetric matrix by construction. This is its spectral composition. Because these vectors are linearly independent, these singular values will both be strictly greater than 0. So that means that the matrix A transpose A is symmetric, and then we use this symbol to indicate that it's positive definite. So that implies that there's an explicit solution. So that means that I could write the W vector as, I could say that that is A transpose A inverse times A transpose times C. This is the normal equation, and this is a solution of the normal equation. If I needed the vector P, I could find that explicitly too, because I would have P equals A times W, and then I substitute this known W in, and I get that that projection vector equals this big long result, A times A transpose A inverse times A transpose times C. And this is sometimes written as a projection matrix times C. And so what we have is this. We started out by having two basis vectors, a1 and a2, and we were given a new vector c. And we said, well, the nearest point p that's in the vector space spanned by those two basis vectors, that has to have an error vector that's of minimum length. And it turns out that we can solve that for a given c using this projection matrix. Let's observe that this projection matrix, it does not, the matrix itself depends only on the matrix A. That is, it depends only on the basis vectors. And we can just pump any unknown vector c into it, and we can determine what vector p in the vector space is nearest to c. Let's make an observation here that I'll just call this an aside. Aside is that p is not the sum of p1 nearest to a1 and p2 nearest to a2. That is, it is not true that we can simply find the vector p1 that projects c onto a1. So perhaps it'll be, can it be a negative? Oh yeah, it can be negative. So w could be negative here. We can't just find the projection on a1, the projection of c on a2, and add them together. So here's an example that you can work out yourself. You could try a1, and the simplest non-trivial case is a size 3 vector. Suppose you have a1 is the x-axis, and suppose that you have a2 is 1, 2, 0. This will span the xy plane. If you then take a vector c, which is 1, 1, 1, then by geometry, the nearest point p that's in the xy plane is, you would just drop that bottom entry. But what you'll find is that if you project c onto a1 and then c onto a2 and add them together, you won't get the same answer. So this is a good exercise for you to do. You can even do this by hand, and what you'll discover is that the projection is not the sum of the projections. The projection involves both of them simultaneously.